Hello and welcome to the first of a series of videos about some basic mathematics that we'll be relying on for most of the rest of this module. Starting off with the concepts of frequency, and in particular the difference between frequency in hertz and frequency in a unit that you may not have come across, radians per second, which turns out to be, in most cases, more useful. Firstly, what do I mean by frequency? Well, many of the waveforms that we're dealing with in this module are repetitive, in the sense that they exactly repeat themselves. The minimum period, the minimum time after which a waveform exactly repeats itself is known as the period. In this case here, I've labelled it as t. Means that if the waveform has any particular value at any particular point, if I move capital T forward in time to there, the waveform would have exactly the same value. And that would be true no matter where I start on the waveform. I move forward in time by t, and it has exactly the same value. And t, the period, is the minimum possible time for which that is true. It's clearly also true for multiples of the period. This, for example, is 2t, twice the period. And if I move forward by 2t, I end up at exactly the same value as I had before. But 2t is not the period because 2t is not the minimum time that I have to move in order to get to exactly the same place that I was before, no matter where I start. So that's t. That's called the period. The frequency in hertz is 1 over the period, 1 over t. But there's another way of specifying the frequency, and that's in terms of something called radians per second, which I usually write as a lowercase Greek omega, like this. And that is to define the frequency in radians per second as 2 pi divided by the period. So, the frequency in radians per second is 2 pi times the frequency in hertz. Why, you might ask, do we have such a strange definition of frequency when defining the frequency as 1 over the period and giving it the units of hertz seems much more intuitive and reasonable? It's because the mathematics of dealing with frequencies works out much easier if we're dealing with angular frequencies in radians per second. Let me illustrate a bit more about the difference between these two frequencies. Here we have a dot moving around a circle, and it moves around the circle with a frequency. After a certain amount of time, it ends up back exactly where it was, and the minimum time after which it ends up exactly where it was, is known as the period, or t, and the frequency in hertz is 1 over t. In this particular case, the period is from that long, so the period is about 4.5 seconds, and that makes the frequency 1 over 4.5, which is about, well, 2/9 hertz. What about radians per second? One of the reasons that radians are so useful is because it makes it very easy to relate how fast you are going to the angle subtended by the dot against this axis, the horizontal axis here. I'll just pause it for a bit, it gets a bit distracting. This dot here, if I drew a line from the origin to the dot, it's currently subtending this angle to the horizontal axis. That angle looks like it's about 60 degrees. Okay, bit longer, bit bigger than that now, about 68 degrees. Now, supposing I wanted to work out what the length of this arc was from here to here. I've drawn it in blue here. The length of that arc is 68/360ths of the way around a circle. The circumference of a circle is 2 pi times the radius. That's all the way round. There are 360 degrees all the way round the circle. So here we've gone 68 of those 360 degrees, which is a factor of 68/360 of the way around the circle. So I wanted to work out what the length of this arc was. I would have to do this calculation. The radius here, the length of this line to the dot, multiply it by 2 pi, multiply that by 68 and divide by 360. It's a bit of an annoying calculation to do. However, I could measure the angle in radians rather than degrees. If I measure the angle in radians, then it would no longer be 68 radians, it would be 68 divided by 360 times 2 pi radians. So if I had that angle in radians rather than in degrees, to work out the length of this arc here, all I would have to do is take my angle in radians, I'll call it theta radians, and say theta times r is the length of the arc. Much easier calculation. We tend to use Greek letters for angles in radians, just like we use Greek letters for frequencies in radians per second. So that's radians, angles. What about frequency? Well, frequency is measured in radians per second. It's the number of radians that you go through per second. There are 2 pi radians in one complete rotation. Therefore, if I am going at f hertz, I am going f rotations, f complete rotations per second. Each rotation is 2 pi radians. So if I'm going at f rotations per second, I'm going at 2 pi times f radians per second. And that is angular frequency. 2 pi times the frequency f in hertz. It's the number of radians that this dot is going through per second. We'll see a lot more examples of that later on. In fact, you'll probably get a bit tired of multiplying things by 2 pi, because people still tend to specify frequencies in terms of hertz. But usually, when we're dealing with them in this module, it's the frequency in radians per second that we want to know. I'll just set this going again and flip over so that we can see the angle in radians. You see that the right angle, 90 degrees, is pi over 2 radians. 180 degrees is pi radians. 270 degrees is 3 pi over 2 radians. All the way round is 0 radians or possibly 2 pi radians. This demo is available linked on the website. Do download it, have a go, play around with it, and let me know of any ideas for improvement. Okay, that's the end of this first little talk. Next time we'll be looking at averages.